All right, everybody. So this is your answers video for the waves and sound review. And I skipped over all the definitions because, again, you can find those in your notes or on the internet or watching the puzzle videos from the past lessons. So let's just jump in with number 2. So number 2 says the figure to the right, this diagram, shows a wave of a certain on a string at a certain instant. The oscillator that sends out the wave is vibrating at 120 hertz, and we're supposed to find various things. So we have to just measure some of these things using the graph. So it gives you a note here. It says on the x-axis or the horizontal, it's in centimeters, and the y, it's also the y, it's millimeters. So we just want to make sure we take notice of those units. So wavelength is measuring from crest to crest or trough to trough or identical part to identical part. So this is like 2 to 6. So I would say that the difference between 2 and 6 is 4. So it would be 4 centimeters in length of the wavelength. And remember, the wavelength symbol looks something like that. So we don't work in centimeters very often, so that would be 0.04 meters, and we're going to use that later on when we get to calculating the speed. So, but if you said 4 centimeters, that is correct. The amplitude, you're just measuring from the equilibrium position up to the top of the wave, so it looks like it's going up to about 0.1, so this would be 0.1 millimeters, so it's a pretty small wave for that one. For C, you calculate the period of oscillation. The period is the inverse of the frequency, so it would be T equals 1 over F. 1 over F. So that would be 1 divided by the 120. And if you put that in your calculator, you get 0.00. And then an 8 and a 3, and the 3 is repeating, which you don't have to worry about, but that's how many seconds, so that's that part. And then finally for part D, we're trying to calculate the speed of the wave, so V equals F lambda. So you're taking the frequency and multiplying it by the wavelength. So the frequency is at 120. And then we want to use the wavelength in meters to get it into meters per second, so 0.04 times 120, that's going to get you 4.8. So 4.8 meters per second should be the speed of the wave, which is the first question on this review. All right. For the next one, this is talking about superposition. So these two wave pulses are going to like move towards each other and overlap in all these cases in A, B, C, and D. And we're trying to decide, we're going to rank them from the biggest positive to the biggest negative in terms of their amplitude. What I'm going to do first, it also says state the type of interference. So constructive interference versus destructive. Constructive, they add together to make it bigger. So A, they're going to add together to make bigger. C is also going to be constructive. Destructive interference occurs when they add together and make a smaller wave. So they're reducing each other. So if you think about these two, when you add these two together, you just kind of look at the heights. So these two heights, if you add those two heights together, that's going to get you a wave that's, pretty big. And these are adding together and they're equal, so they're going to cancel out. So it's just going to get you a flat line. These two are shorter. So if we add the two shorter ones together, we still get a bigger wave, but it's not quite as big as this first one. And the last one, you're taking the big and the small, and you actually end up with a negative wave kind of on this one. So you get a small negative wave. So from biggest to smallest, biggest positive would be A. The next biggest positive would be C. Then B would be next because that's 0 because they just cancel. And then finally D would be the biggest negative. So this is the most negative on that side, and this is the most positive in terms of their amplitudes on that side. Continuing on, the next question is just asking you to kind of compare and contrast mechanical waves, non-mechanical waves, transverse waves, longitudinal waves, draw, sketch, label, parts, examples. So mechanical waves, mechanical waves and non-mechanical waves are actually really similar in many cases, so it's easier to distinguish between them. Mechanical waves need a medium, so they need a thing to travel through, so they need something to vibrate, some particles. So examples of mechanical waves: a wave on a string, a wave on a slinky, sound, anything that's vibrating some sort of particle, that's a mechanical wave. Non-mechanical waves, they're the opposite of mechanical, so no medium. They don't need a medium. So they don't need to travel through any substance. And the example of non-mechanical waves would be electromagnetic waves, including light. So light is the non-mechanical wave we are most familiar with and studied a little bit in this unit. For transverse and longitudinal waves, those are two types of waves, so I'm going to draw them kind of going across here. So for the transverse wave, that's the one that has sort of the bumps. It's like kind of your traditional looking wave, so that would be my picture of it. The wave motion, the wave moves perpendicular. So I'm still on motion. It's perpendicular to the vibration, and perpendicular means at 90 degrees. So this wave is actually going across like this, but the vibration is perpendicular to that. So this would be an example of like we take the slinky and we shake it up and down, and the wave makes that bumpy pattern, but the energy of the wave is carried across, but the vibration is actually up and down. In transverse waves, we have crests, which are the tall parts or the highest points, and the troughs, which are the most negative points. So that's your crest and trough, and they keep repeating themselves in these sections. Again, they all have the same ideas. They have frequency, and this is mechanical, non-mechanical, transverse, longitudinal. They have frequency and wavelength. They have amplitudes. They have all the kind of wave behaviors. They just, there's two different forms. So the next one is a longitudinal wave, and longitudinal waves are a little harder to picture, but the motion is parallel to the vibration. So that's the symbol for parallel in math. So when it's parallel, what that means is the wave motion is moving that way, so the velocity of the wave is moving to the right, and the particles actually shake back and forth to the right and left. So for this, if you imagine the slinky and we pull the slinky coils together, you get what's called a compression. And then the other parts that are kind of stretched out, those are rarefactions. And we can keep, if we keep oscillating or causing that compression and rarefaction to alternate, so we keep like adding in more compressions and rarefactions, that's what happens. Sound is a example of a longitudinal wave. Transverse waves, waves on a string. You could do both of these with the slinky, which if you're in class, I do that. So that's those definitional kind of questions there. All right, so for the next one, we're going to have light refracting as it enters a new medium. The light is starting in water with an index of refraction of 1.3, and it's ending up in air, which is an index of 1. So it's going to go from a more dense to a less dense. So when that happens, it speeds up. So we should expect that the wave is going to go faster. And when it speeds up, the wave bends away from the normal. So that's what I would expect, is that this angle that we measure here, which is the angle of incidence, so that's going to be 40 degrees. That initial angle that the ray forms with that normal, remember the normal is the vertical line here. This ray that it bends at is going to be bigger, so I'm going to expect this angle to get bigger here. And let's go ahead and calculate that angle, and then we can draw it in properly. So the equation we're going to use is Snell's law, so it's n1 sine theta 1 equals n2 sine theta 2. So if we plug in the values that we have in this problem, it would be the first index is what we start out in, the second index is what we end up in, so it would be 1.3, and the index is just the number that represents the material and the ratio of the speed of light in the material to the speed of light in a vacuum. So coming back to this, 1.33, that's what we're starting in. Sine, we got to measure this angle, so if you count that off, it's 40, and I already said it was 40, so that's 40 degrees. That's equal to the new index, which is just 1, because it's going into air, which has an index of 1, and then the sine of theta 2. So you're going to get a number here, 1.33 times the sine of 40. I didn't write that number down, but then you're going to take the inverse sine of that, and you should get theta 2 is something like 59 degrees or so. So 58.7, but you can just round to 59. So this refracted ray is going to bend away from the normal. So it's going to go pretty close to the 60. So that angle there is bigger than this angle that it started out with. And that should happen because it's going to speed up when it goes into a less dense medium and it's going to bend away. To calculate the speed of light in water, N is equal to C over V. So V is the speed of light in that medium, and we're going to solve for that. So it would be 1.33, because that's the index in water, equals the speed of light, which is 3 times 10 to the 8th meters per second, over V. So we basically cross multiply and solve, and you basically take 3 and divide it by 1.33, and then you take that number and you multiply it by times 10 to the 8th. So if we do that, 3 divided by 1.33, we'll get something like 2.25. So it is definitely going slower in 2.25 times 10 to the 8th. Don't let me forget that part, meters per second. So it's still going really fast, but it's going a lot slower than it does in just a vacuum, or basically air is close to a vacuum, so 3 times 10 to the 8th. So it's slower. So it's slower, it's closer to the normal. When it goes faster, it moves away from the normal. All right. Similar question, this time we don't know the index that it's going into. So it's starting in water, it's ending up in some glass here, and we don't know that number. If the angle of refraction when entering the glass is 20, so this again is the same angle that we had before, which is 40. I'm going to draw in the 20, so 20 would be maybe like there. So this angle that it refracts to gets smaller. So because the angle gets smaller, we would expect it to slow down. So it's going to slow because it bends towards the norm. So when you go slower, you bend towards something. If you're faster, you get away. That's my kind of way that I remember it. So we're going to calculate the index. So we're going to figure out what is this N2 number. We're going to figure out how fast the speed of light is in that material. So we're going to find the velocity of N2. And then we're going to talk about kind of comparing the speed of light in water to the speed of light in this glass. And we'll see that it is definitely going slower in the glass. So, and when it goes slower, it bends towards. So for the index of refraction again, and the index, we're going to use the same equation, Snell's Law, and N1 sine theta 1 equals N2 sine theta 2. And we're going to plug in the values. So we got 1.33 sine of 40. Make sure you're in degree mode. And then N2 is what we're solving for. That's the mystery. And then sine of the new angle, which is 20 degrees. Okay. So when we divide by sine of 20 on both sides, or you just get sine of 20 in your calculator, it's a decimal, you divide through and you do it in your calculator, you'll get N2 is something like 2.5. So you get 2.5 is the new index for N2. And to calculate the speed, we're going to do C over V again. So it would be 2.5 equals 3 times 10 to the 8th, the speed of light, over V in the glass. So the velocity in the glass ends up being close to 1.2 times 10 to the 8th meters per second. So in the glass, it's 1.2. We said in the water, it was 2.25 times 10 to the 8th. That's what we got for B in problem 5. So it is definitely, again, slowing down. It's going from 2.25 to 1.2. So it slows down and it bends towards. So that checks out with what we got for that answer. Couple other questions left. So we're down to the last two. Doppler effect is that apparent change in frequency from the motion of the source or the observer. So if you want the frequency to increase, you're going to have to get things to move together or closer. So move together. So there are 3 ways that you can get the waves to kind of get jammed together. And they are for the source and the observer to move. So for the 3 possibilities, you could have your source moving towards your observer. So the thing that's making the noise it's moving closer to the observer, and that's going to make the frequency appear higher. So that's like the police car moving towards the person who's stationary. We could have the source being stationary and the observer moving towards the source. This observer is moving towards this source, and the frequency is going to sound higher. Or you could have both of them moving towards each other. So the source is moving towards the observer, and the observer is also moving towards the source. So all of those things increase the frequency, and that's because the waves are shoved together. So if you may imagine the wave patterns, they are getting shoved together. So that's a higher frequency. The opposite is true if we want a frequency to be a lower observed frequency. So we want them to move apart or spread apart. And you could do this, again, 3 separate ways. And it's the same kind of ideas, it's just in the opposite kind of direction. So if we had a source that moved away from our stationary observer, the wave pattern would be further apart, so that would be a decrease in frequency. We could have our source be stationary, and we could have our observer moving away. That could be another option. Or we could have both of them move away from each other. So those are the 3 possibilities to make the frequency lower. All right. The last question is dealing with standing waves. So a standing wave pattern is being produced on this string, and the string has a length of 10 meters. Okay, so it asks first off how many antinodes are present, and then how many nodes are present, and then we're going to figure out the speed of the wave if we know the frequency of the wave. So same kind of ideas, just standing waves. Antinodes are the points where it vibrates the most, so that's like these points. So when you're looking at the football pattern, it's like the middle of the football. So there are 4 of those present. The antinodes are where the wave is like destructingly interfering. So like there's no motion here. So all these points where it's on the equilibrium. So I'm putting these circles there. Those are nodes. So those are nodes. These are antinodes. So 1, 2, 3, 4, 5 of those in this pattern. And then in order to calculate velocity, it's the same equation. It's frequency times wavelength. So we have to figure out the wavelength that is fitting on this string, or the length of one wave. So the frequency is easy. That's just 6. It's given to us. The wavelength you got to think about in terms of the length of the whole string. So the whole string is 10 meters. And for this wavelength essentially is going from 1 complete cycle. So that looks like that's 1 cycle. That looks like it would be 2 cycles. So so there are 2 wavelengths on this pattern that fit on the string. So if we divide by 2, 10 divided by 2 is 5. So 5 is going to be the wavelength of the string. And when you plug in 6 times 5, you get 30. So 30 meters per second is how fast the wave is actually traveling on the string. So that's the last answer. So if you can do this review, you should be fine on the test. So good luck to you guys, and I will talk to you later.